during the last lecture, we learned all about ions and ionic compounds and how to name them. This lecture focuses on covalent compounds, which is when you have two nonmetals sharing electrons, forming different kinds of compounds, right? And these are all going to be binary, meaning they have only two elements, carbon and oxygen here, sulfur and oxygen, nitrogen and oxygen, nitrogen and fluorine, always two different nonmetals. And because some of those elements can combine in different ratios, that's the law of multiple proportions, like nitrogen can be in a 2-to-1 ratio, or in a 1-to-1 ratio you can have NO or NO2, right? So that was the example used in chapter 3, I can't recall, or 2, where we had the law of multiple proportions, right? So, but similarly to when we had different charges, we communicated that with Roman numerals. Here we are going to communicate how many we are by prefixes, right? We're gonna, if we have 2, we call it di. If we have 3, we call it tri. If we have 5, we call it pent, like the pentagon. And so we're going to use some prefixes to indicate that, right? Because we don't have charged particles here. We're sharing, right? So we got to use a different method. And that's why you always have to remember, before you name something or before you determine a formula, is this ionic or covalent, right? Okay. Here's an interesting fact, and this was completely made up, of course, just like all of chemistry is completely made up. The order of the elements in a formula, right? Why is it CO2 not O2C, or N? Why does the N come in front of the F? It's because of this, made up in this case, order. Okay, so there's an order that the nomenclature people came up with, right? So first you name carbon. It's group 3, then group 4, then group 5, then hydrogen, then group 6, group 7, right? Group 3 is boron. So you've got boron, and then carbon group, nitrogen group, then hydrogen, which is group 1, but it fits in differently, and then this is oxygen, and then fluorine. This is the oxygen group, so there you go. We are only inserting sulfur, so this is why sulfur comes before oxygen. So this is sulfur and below. And then fluorine, chlorine, bromine is of course group 7. So this is again chlorine and below, sulfur and below. And then oxygen and fluorine are always last. That's why you get NF3, right? N is group 5, F is always last. S is group 6. But O always follows group 6. And so this is why we have the order that we do. Okay, so that's just an interesting little thing here, right? So rule, we have the first element, we just give it its name, like carbon or sulfur, and then we name the second element, and it's just like we did for the ionic compounds. It gets the ending IDE. So we have carbon, and oxygen would be carbon oxide. And then we can of course have carbon monoxide or carbon dioxide, right? And so this is where the prefixes come in, and they're on page 2. They're not on page 278. They are on, as far as I know, on page 68. Okay, so this is comes from an old book, right? It's obviously in chapter 4. Now I'm confused, but anyway, you can look that up. But the prefixes are also here: mono, di, tri, tetra, penta, and so on and so forth. 1, 2, 3, 4, and 5. And mono you don't use for the first element, okay? But you do for the second. So this is carbon monoxide. It's not monocarbon monoxide. So you don't need it for the first one, but you do need it for the second one if it's just one. Okay, so that's the only odd thing in my opinion with the prefixes. So then, knowing the prefixes, mono, di, tri, tetra, penta, hexa, we will not go beyond hex here in this class. So we have carbon, single element, Of course, if you have more than one, you do give it the prefix. Okay, so no, only if you have a single atom as the first, you don't use the prefix. If you have more than one, you use the prefix. For the second element, you always use the prefix and then the IDE ending. Seen this already. This is chlorine, which turns into chloride. 4 is tetra, so tetra, and then chloride. Okay. Phosphorus, we have 2 of them, so di, phosphorus, R. And 5 is penta, pentaoxide. So oxygen turns into oxide. Here's a sulfur oxide. It's a sulfur tri, standing for 3, oxide. Really not that hard. Here's nitrogen oxide. We have 2, so it's dinitrogen oxide. I'm trying to write quickly, but when I do, I of course become pretty sloppy. I have terrible handwriting, but all of this can be looked up as well. Dinitrogen oxide. Jesus. Sorry about that. Oh, here are the names. And what did I do? I made a mistake, right? Here you go. The dinitrogen monoxide. Okay, so since I made this mistake, I won't hold you responsible either. Let's give these things some formulas. This is not difficult. Boron, find it on the periodic table. It's a B. Fluoride, fluorine is an F. Tri means 3, so it's BF3. Sulfur, pentachloride. Sulfur is F. Chloride is Cl. Penta means 5. And then tetra, sulfur, tetranitride. So we have sulfur 4 and nitrogen 4. Again, these are always going to be binary. We just have 2 elements. Don't confuse it with the polyatomic ion. Don't throw any Roman numerals in there. And that is it. We have some other things that we name that follow different rules. For example, acids. There's a lot of the polyatomic ions like nitrate here and chlorides. They can combine with a hydrogen, right? So hydrogen can also lose an electron, right? So you remember hydrogen is a nonmetal and we expect it to share, but a lot of times it can also lose and become ionic, and when it does that, it usually becomes acidic, or it can be an acid. Okay, so when H plus combines with nitrate, ATE, then you get nitric acid, right? Nitric acid. So you got a polyatomic ion, and so if you have sulfate, ATE, you get sulfuric acid, right? So this is if you have an ATE ion, you end up with an ic acid, like sulfuric acid, nitric acid. If you have an ite, right, like one nitrite or chloride or sulfite, ITE, you turn your acid into a sulfurous acid. If it's sulfite, ITE, sulfurous acid. Or here we have chlorous acid, HClO, right? Again, we have the polyatomic ion here combining with H plus, which makes acids. And so we have hydrochloric, that's on the next page. We have those depending on the polyatomic ions. We also have hydrogens or H pluses that combine with simple anions like chloride, iodide, right? So HCl is hydrochloric acid, okay? And so that's it is a hydrogen chloride when that's how you would of course name it when it is a gas. But if you bubble that gas into water, you get aqueous HCl, and then now you have acid strength, right? The polar bonds of water are going to rip the H plus and the Cl apart, and you get free flowing H plus, which makes a solution acidic. So this is muriatic acid, which you can actually buy at a hardware store, and it's a strong acid. It's very corrosive. And So hydrochloric acid aqueous here, hydroiodic acid here, single elements with hydrogen. That's when hydrogen combines with either a polyatomic ion or a very electronegative element. Electronegative element like chloride or fluoride. We have so-called hydrates, and you will deal with one in the lab. You are going to dehydrate a hydrate. This is later on in the semester, I don't remember now. Either way, what we have is we have an ionic compound where the difference in atomic size of the cation and the ion is rather large, and so it doesn't pack as efficiently, and there are some gaps, and so water molecules can get in there, and anything from 1 to up to 7 water molecules can trap in the crystal lattice. And so here for copper sulfate you have 5 water molecules. So this would be, of course, this is an ionic compound, right? So you name it like you always would. So this is copper sulfate. It's ionic. Copper can have different charges. So sulfate's -2. Therefore, this has to be copper 2 sulfate. But since it's hydrated, we call it a hydrate, and so there are 5, so we use that prefix pentahydrate. Okay, so this was acetate, sodium acetate. This is 1, so we call it monohydrate. So this is sodium acetate. Sodium acetate. Monohydrate. Hydrate. Okay. Hydrate. Okay. Okay, so I was going to just say, since we talked about acids, and I said this comes from vinegar, acetic acid, right? So if it combines with C2H3O2, it's actually acetic acid, okay? Acetic acid, which is a weak acid. No big deal. Alright, shifting gears somewhat, we've already looked at molecular weights. We're going to take that one step further now. Here's just a review. We can have molar masses and formula masses, and of course this is all based on having 1 mole of something, right? So the molecular weight of water is of course 18 grams per mole. 1 atomic mass unit, if you do it on the basis of atomic mass units, it's less useful, but if you remember, look at the periodic table. All you do is you look up the average molecular mass here. Hydrogen is 1.02, oxygen is 16. You add it all up, you get 18.02 AMU, which is of course, and this should be 18 here, not 8, and that turns into 18 grams per mole. This becomes a conversion factor, right? And so if we were to calculate the formula mass or molecular weight of C6H12O6, we need to find the average mass of carbon, hydrogen, and oxygen. So here we have hydrogen already and oxygen, and carbon is 12. And then all you need to do is multiply that out, right? We have 6 times the atomic mass of carbon times 12 times the atomic mass of hydrogen plus 6 times the atomic mass of oxygen. You add it all up, you get to 100.16 AMU. You turn that into grams per mole if you want, and to get the molecular weight. So this is just a formula mass. You report that as AMU. Or a molecular mass would be 180.16 grams per mole. Calculate the formula mass of calcium nitrate. For that you have to of course first come up with the right formula. Calcium nitrate is CaNO3. Look up on the periodic table calcium. I'll backtrack a little bit. Calcium is 40. nitrogen is 14, oxygen we have. And then, hey, I thought I had that there. Oh, I was going to, okay. So then you just have to do 1 times 40 point, I don't remember that now what that is, 40.08 plus 1 times 14.01 and plus 3 times 16.00. And I don't know, I don't have a calculator, I don't feel like it. Soup. And then if we do molar masses, we have, for example, using the molar mass to count molecules by weighing. Okay, so again, we scale this up so we can actually figure something out on the balance and not just weigh out 0.00000, 26 different little zeros here. Okay, all right, so carbon is 12, oxygen is 2, so we get a molar mass of 44.01 grams per mole. They set that up here as a conversion factor. And so then you can take the grams, if you have 12 grams of carbon dioxide or 150 grams of carbon dioxide, right? So let's say you have 150 grams of carbon dioxide and you want to figure out the number of molecules. This is a two-step conversion. First you go from grams to moles, and then you go from grams to molecules. From moles to molecules by using the Avogadro's number. So at 1 mole of anything we'll have 6.022 times 10 to the 23 molecules or atoms, whatever it is. And so if you have 150 grams of CO2, you first multiply by 1 mole, divide by gram, and then you multiply by molecules of CO2 divided by 1 mole, and you get an answer of molecules here, right? So two-step conversion. You go from grams to moles, and from moles to molecules. Okay, because it's related, it's using that. I'm using an example. Instead of 150, I'm using 8.5. So 8.5 grams divide, multiply Avogadro's number. It's the same thing, not with 150. I don't want to re-record, so it is what it is, and you get a number of 1.2 times 10 to the 23 molecules. When we come back, we're going to do percent compositions.